Most species on Earth will never discover the precious secrets hidden inside stones. You usually need tools to crack them open and reveal what lies inside. In the same way, four-dimensional geometry remains a mystery to most people. But there are tools that let us uncover the treasures hidden in four dimensions, and it turns out that four dimensions are one of the most fascinating settings for geometry. Compared with three dimensions, the possibilities multiply dramatically, and beyond four dimensions, there are less symmetries that lead to convex and uniform solids. Join me on an archaeological journey into the world of four-dimensional geometry and let us uncover the convex shapes generated by reflections of mirrors in Euclidean space. When we want to understand objects in four dimensions, a common strategy is to begin with similar objects in lower dimensions. Many of you have probably already imagined spheres or cubes in four dimensions. Let's start with the family of cubes. In one dimension, a cube is just a line segment connecting the points with coordinates 0 and 1. In two dimensions, we get a square with four vertices at 0, 0, 1, 0, 1, 1, and 0, 1. Likewise, in three dimensions, the cube is defined by vertices with the following coordinates. By now, the pattern is straightforward to see. The vertices of a cube in any dimension are given by all possible combinations of zeros and ones. In four dimensions, we find 16 vertices that form 8 cubes, which together make up the four-dimensional tesseract. While this step-by-step approach into four dimensions is convenient, it also has clear limitations. It only reveals objects that already have analogues in three dimensions. For that reason, it is better to generalize the underlying construction principles. These principles take the form of mirror configurations and reflection groups. In three dimensions, there are three non-trivial mirror configurations that produce convex and uniform solids. In four dimensions, there are 5 non-trivial configurations. Clearly, something new happens in four dimensions. And this is exactly what this presentation is building towards. As a bonus, we will rediscover all 6 Platonic solids that appear in four dimensions. 5 are siblings of the 5 Platonic solids in three dimensions, but one is new. The A series provides a gentle entrance into the world of Coxeter-Dinkin diagrams. It begins with the simplest possible reflection setup and gradually grows into more elaborate forms. It shows the same principle in every dimension. A configuration of mirrors generates a whole family of shapes, and moving the seed point changes the resulting polytope. In one dimension, the story is almost embarrassingly simple. A single point-like mirror splits the line into two halves. A seed vertex and its reflection generate an edge. If the point is moved onto the mirror, the edge collapses and nothing remains. There is no mystery here, only the first glimpse of how reflections build geometry from almost nothing. And this one-dimensional edge will be our tool attempt to build polytopes in two dimensions, which are commonly called polygons. In two dimensions, the line in the Coxeter-Dinkin diagram encodes that the two mirrors meet at 60 degrees, and the reflections generate a hexagon. If the seed point sits on a mirror, the hexagon degenerates into a triangle. This is a nice pattern to keep in mind. When the seed point is moved onto a mirror, the resulting object simplifies. The most complicated polytope is always obtained when the seed point is in the middle of all mirrors. Before we head towards three dimensions, we have to discuss yet another polygon that is generated by orthogonal mirrors. The corresponding Coxeter-Dinkin diagram is shown here. The orthogonal mirrors generate a square. And when the seed point moves towards a mirror, the square collapses into an edge and is no longer a polygon. Translating the Coxeter-Dinkin diagram for the three-dimensional case, we infer that two mirrors are orthogonal, since the first and last node are not connected by a line. The middle node is connected to the other nodes, therefore the next mirror is tilted by 60 degrees with respect to the other mirrors. This configuration of mirrors leads to the truncated octahedron, when the seed point is placed in the most generic position. From there, the object can be deformed into several familiar children. The truncated tetrahedron and the cube octahedron appear along the way, and the process eventually reaches the Platonic solids named octahedron and tetrahedron. In the left panel you can see the two-dimensional constituents. This is also the first place where it becomes useful to think in terms of nets. A polyhedron is not just a solid in space, it can also be unfolded into a flat arrangement of faces. It teaches us to read shapes both as rigid objects and as a collection of boundary pieces. The boundary structure is especially important. If one node is removed from the Coxeter-Dinkin diagram, the remaining diagram describes one of the lower dimensional boundary objects. This is not an accident. It means the Coxeter-Dinkin diagram is not just merely a label for the polytope, but a compact recipe for its whole combinatorial structure. In other words, the diagram tells us not only what the solid is, but also how its pieces fit together. We have to quickly look at two other trivial configurations of mirrors. The simplest configuration corresponds to three orthogonal mirrors. They generate a square prism. You might want to call it a cube. At this point, I have to tell you that different mirror configurations can lead to the same shape. For this presentation, I want to call all objects that are generated by disconnected Coxeter-Dinkin diagrams prisms and color them in gray. Similarly, each polygon can be converted into a prism by a third orthogonal mirror. An example is shown here for the 6 and 3 prism. The Coxeter-Dinkin diagram of the group A4 is where the story expands into 4 dimensions. When the seed vertex is located in the middle of all 4 mirrors, 120 images will be generated that form the edges of an omnitruncated pentachoron that is surrounded by 10 truncated octahedra and 20 hexagonal prisms. At each vertex, 2 truncated octahedra and 2 hexagonal prisms meet each other. Have a look how much space there is left in between. So the three-dimensional surface is rather strongly bent into the 4th dimension. We cut the stereographic projection into parts to reveal the hidden shape. You can find more details on the ideas behind the stereographic projection in the first video of this series that is linked in the upper right corner. Now we can transform this largest shape into any other possible shape that is symmetric with respect to the arrangement of mirrors. There are more possibilities to move the seed vertex onto mirrors, pairs of mirrors, or even triples of mirrors. Consequently, there are many more shapes than in 3 dimensions. The smallest is also a Platonic solid in 4 dimensions. It consists of 5 tetrahedra, that's why it is called pentachoron, similar to the tetrahedron that is composed of 4 triangles. If you chop its corners and then cut along the edges and somehow cut along the faces, you get back the full omnitruncated pentachoron that we started with. As we did in 3 dimensions, we repeat the transformation of these shapes when they are unfolded into nets. All 4-dimensional polychora can be unfolded into 3-dimensional nets. This makes it possible to represent them faithfully in the same way as a cube can be represented faithfully by its net on the cardboard. You can always cut it out and fold it back into a cube. Similarly, these nets could be folded into the 4-dimensional polychora. This is about all you have to digest. We will now repeat the same animations for 2 more families that have counterparts in lower dimensions, before we are ready to introduce the new stuff that only exists in 4 dimensions. If you followed along so far, you can relax and enjoy the enormous beauty that unfolds in 4 dimensions. Otherwise, if you still struggle with the concepts, no big deal, there will be 4 more repetitions of the same ideas. For the B series, we will follow a path that is largely analogous to the one before. The one-dimensional case doesn't require further discussion, as it behaves exactly as in the previous setting. In 2 dimensions, however, a subtle but important modification appears. The label 4 above the edge indicates that the mirrors meet at an angle of 45 degrees, that is pi over 4. So you can see that this choice of label is not arbitrary. It naturally arises when mirror angles are expressed as fractions of pi. With this configuration, the seed point generates an octagon, which degenerates into a square when certain edges collapse. In this way, we get a second representation for a square. The yellow square originates from this degenerate octagon, where half of the edges have shrunk to 0 length. By contrast, the other square arises trivially from reflections across orthogonal mirrors, corresponding to a disconnected Coxeter-Dinkin diagram. Passing from A3 to B3 can be visualized as a slight tilting of one mirror. This modification increases the number of generated images to 48, whose convex hull forms a truncated cube octahedron. Because the diagram is no longer symmetric, there are now more ways to deactivate individual mirrors or pairs of mirrors. Consequently, a richer family of symmetric solids emerges. Among them are the truncated octahedron, the rhombicube octahedron, and the truncated cube, as well as the smaller representatives, the octahedron, the cube octahedron, and eventually the cube. On the left-hand side, one can again verify that every Coxeter-Dinkin diagram obtained by removing a single node contributes a facet to the boundary of these polyhedra. Repeating the construction with the corresponding nets reinforces this observation. In particular, it's worth paying attention to the 2 distinct types of squares. One arising from a disconnected diagram, and the other, the yellow one, from a degenerate octagon. All of these solids, together with several prisms, serve as building blocks for the 4-dimensional polytopes generated by the mirror configuration B4. In the non-degenerate case, 384 image points are produced, forming the vertices of an omnitruncated tesseract, a 4-dimensional analog of the cube, truncated at its vertices, edges, and faces. At each vertex, one finds a truncated octahedron, a truncated cube octahedron, a hexagonal prism, and an octagonal prism. As before, moving the seed point towards mirrors or their intersections produces a sequence of degenerations yielding smaller polychora. The simplest among them are the tesseract and the orthoplex, which are the natural 4-dimensional analogues of the cube and the octahedron. Both are Platonic solids in 4 dimensions. The tesseract consists of 8 cubic cells, while the orthoplex is composed of 16 tetrahedra. At this stage, it becomes again clear that different Coxeter-Dinkin diagrams can lead to the same geometric object. In particular, cubes and octahedra admit multiple diagrammatic constructions. This degeneracy gives rise to a remarkable new Platonic solid with no 3-dimensional analog, the 24 cell, composed of 24 octahedra. It appears here for the first time within this mirror configuration alongside the tesseract and the orthoplex as one of the simplest 4-dimensional polytopes in the B4 family. The A and B series do not stop in 4 dimensions. On the contrary, the patterns we have encountered extend naturally into higher dimensions, where they continue to generate ever more intricate polytopes. If the richness of B4 already feels demanding, the next group type, the H family, elevates both complexity and beauty to a new level. It opens quite literally a gateway to a kind of geometric paradise. Interestingly, unlike the A and B series, the H family terminates in 4 dimensions. But let us proceed step by step. The one-dimensional case offers nothing new, so we move directly to 2 dimensions. Here the mirrors meet at an angle of 36 degrees or pi over 5. The resulting reflections generate a decagon, which degenerates into a pentagon in the limiting case. A pleasing though still familiar outcome. In 3 dimensions we introduce a third mirror as before. and get the full family of polyhedra with icosahedral symmetry. These are noticeably larger and more intricate than their tetrahedral and octahedral counterparts. Beginning with the truncated icosydodecahedron, successive degenerations lead us down to the icosahedron and the dodecahedron, two of the classical Platonic solids. As before, we repeat the top-down transformation of these polyhedra in the representation of their nets, and you can nicely observe how decagons turn into pentagons and hexagons turn into triangles when the seed point is moved onto mirrors or intersections of mirrors. The transition to 4 dimensions, however, marks a dramatic escalation in complexity. The sheer variety of resulting geometries pushes the limits of visualization. A complete survey involves objects with hundreds of thousands of faces. Despite this explosion in detail, the underlying structure closely mirrors that of the B4 configuration. In particular, the number of distinct geometries remains the same. At the top of this hierarchy sits the 4-dimensional analog of the truncated icosydodecahedron, the omnitruncated 600 cell, also known as omnitruncated hexacosacoron, with its staggering 14,400 vertices. Unlike in the previous series, each Coxeter-Dinkin diagram leads to a unique solid. That's why we encounter only two Platonic solids, the 120 cell and the 600 cell. All polychora in this family share remarkable fivefold symmetry, a feature that only exists in 2, 3, and 4 dimensions. Why does this family not extend to 5 dimensions? One can certainly write down similar Coxeter-Dinkin diagrams and arrange mirrors in 5-dimensional space, including configurations where two mirrors meet at an angle of 36 degrees. However, such setups no longer produce a finite set of reflection images. A single seed point generates infinitely many images. These images still exhibit structure, with local building blocks resembling the polytopes we have seen, but they no longer fit together to form a closed object. Instead, they fail to close up in Euclidean space. There is simply no way to assemble them without overlaps. To accommodate these structures properly, one must move to the hyperbolic space, where such infinite reflection patterns can exist naturally. In fact, there is, in principle, no restriction on the choice of Coxeter-Dinkin diagram, provided one is willing to work in the space with an appropriate curvature. Check out an older presentation that is linked in the upper right corner of this video. At this point, the proliferation of structure and complexity may feel overwhelming. It is therefore reassuring to note that topologically, these objects remain quite simple. All of them can be understood as intricate patterns drawn on the surface of a 3-dimensional sphere, embedded in 4-dimensional space. For instance, all 14,400 vertices of the omnitruncated 600 cell lie at the same distance from the origin. Seen from afar, the object appears perfectly round. Only upon closer inspections do its elaborate facets come into view. We have finally reached the first mirror configuration that is genuinely unique to 4 dimensions, labeled by D4. Unlike the H family, which culminates in 4 dimensions, the D series begins here. In 4 dimensions, it becomes meaningful to introduce a bifurcating Coxeter-Dinkin diagram for the very first time. For completeness, we show how this branching pattern extends into higher dimensions. The diagram of D4 is remarkably symmetric, and this symmetry has immediate consequences. The variety of resulting polychora is noticeably smaller than in previous configurations. But most notably, the 24 cell makes a prominent reappearance within this arrangement. Another feature worth highlighting is the recurring presence of cubes, marked in gray. Their origin is particularly elegant. Their Coxeter-Dinkin diagram consists of 3 isolated nodes corresponding to 3 mutually orthogonal mirrors. These mirrors align with the outer nodes of the D4 diagram, giving rise to cubes in a very direct geometric way, neatly embedded within the higher dimensional structure. At first glance, This configuration feels fresh and promising. However, a closer look reveals a certain familiarity. Every polychoron in D4 has already appeared in the B4 configuration. This is no coincidence. This symmetry is therefore often described as demi-tesseractic. A concrete example illustrates this relationship. Begin with a tesseract and remove half of its vertices. The remaining structure can be reorganized into a 16 cell, the simplest member of the D4 family. Other polychora arise through analogous reductions. The largest polychoron of P4 has twice as many vertices as the counterpart in D4. We now arrive at the most exceptional case, the F4 mirror configuration. This kind of setup forms regular solids in 4 dimensions only. Once again, the Coxeter-Dinkin diagram is highly symmetric, suggesting a limited number of resulting shapes. But this time, symmetry does not imply familiarity. Several of the resulting polychora are entirely new, and some reach astonishing levels of complexity. Why so large? The answer lies in geometry. The constituent polyhedra fit together with tiny gaps. To close these gaps and form a complete four-dimensional structure, the shapes must grow significantly in size. The largest example is built from truncated cube octahedra and hexagonal prisms. You can try to place 2 of each around a single vertex. You will notice how little space remains. This time cubes are highlighted in blue. Unlike before, they do not arise from simple orthogonal mirror arrangements. Instead, they emerge as degenerate cases of the truncated cube octahedra. At the opposite end of the spectrum, we encounter a familiar surprise. Our new Platonic solid, the 24 cell, appears now as the smallest member of this configuration. At this point, it is hard not to step back and reflect. Why do we inhabit a three-dimensional universe? From a geometric perspective, one might wonder whether higher dimensions simply contain too much structure, too many possibilities to navigate intuitively. Before we conclude, consider one final object. There exists a polychoron composed entirely of truncated cubes. It comes very close to being Platonic, but falls short since the truncated cube itself contains both squares and triangles. Interestingly, a similar almost Platonic structure appeared earlier in the A4 configuration, where truncated tetrahedra played the corresponding role. This is yet another distinctive feature of four-dimensional mirror systems. Highly symmetric diagrams can give rise to structures that nearly, but not quite, achieve Platonic perfection. Since you have followed this geometric journey all the way to this point, you might want to know how these shapes can actually be computed in practice. Let us therefore walk through a concrete four-dimensional example. Once the method is clear, it can be transferred almost mechanically to other settings, including the more familiar three-dimensional cases. To keep the discussion focused, we choose the A4 configuration. Even here, the full group already contains 120 elements, which is more than enough to illustrate the essential ideas without becoming unwieldy. Our starting point is the Coxeter-Dinkin diagram. This compact object encodes all the geometric information we need. Most importantly, the relative orientation of the mirrors that generate the symmetry. To translate this diagram into explicit data, we interpret each node as a mirror with a corresponding normal vector. The edges of the diagram, they prescribe the angles between these normals. The mirrors corresponding to the first and the last node are required to be orthogonal. Apart from this constraint, we can freely choose a convenient coordinate system. So we align the first normal with the x-axis and the last one with the w-axis. The remaining normals are determined by the angle conditions encoded in the diagram. The second normal forms an angle of 60 degrees with both the first and the third, and it's orthogonal to the last. The third normal is orthogonal to the first and forms angles of 60 degrees with both the second and the last. In terms of scalar products, these conditions are expressed as follows. At this stage, the system is still underdetermined. Geometrically, this reflects a residual rotation freedom. The y and z component of the second and third normal can still be rotated without violating the angle constraints. To make things concrete and reproducible, we fix one particular choice. With these normals in hand, the rest is straightforward linear algebra. Each mirror defines a reflection, and the corresponding reflection matrices can be written down directly. In coordinates, this amounts to just a few lines of computations, or if you prefer, a more compact formulation using tensor products. From here, the full symmetry group and with it the entire polychoron can be generated systematically. Now comes the computational core. We generate a matrix representation of the symmetry group. Starting from the reflection matrices as generators, we multiply them in arbitrary order and as often as needed until no new matrices appear. In practice, this closure process is handled by a short Python script. As mentioned in earlier videos, we work with infinite precision. There are a few technical subtleties hidden here, but if anything feels unclear, this is exactly what the comment section is for. The next step is to determine a suitable starting point, often called the seed. We require a point that has equal distance to all mirrors. When some of these ones are replaced with zeros, one gets seed points for smaller shapes. Denoting this point by Q, the seed for the omnitruncated pentachoron satisfies the following equations. Applying 120 group elements to this seed produces 120 distinct points, the vertices of our polychoron. We extract the geometry from this point cloud as follows. We fix the seed point Q and identify its nearest neighbors, those points at minimal distance. In this case, we find 4 different neighbors. Geometrically, each neighbor defines an edge from Q, and each pair of neighbors defines a face with Q, and each triple of neighbors defines a three-dimensional cell that contains Q. To analyze such a cell, we select 3 neighbors, for example P1, P2, and P3. We form the spanning vectors U, V, and W. Similar to the surface in 3 dimensions, this cell is also described by one normal that is orthogonal to the 3 vectors U, V, and W. One way to compute this n is by solving this linear system of equations. A more elegant approach uses a higher dimensional analog of the cross product, expressed via the epsilon tensor. When this is applied, we obtain the normal, given as follows. We don't require normalization for our purposes. With this normal vector in hand, we can identify all vertices that belong to this cell. A point that belongs to this cell has to satisfy the following equation. A short script reveals 24 such points forming the vertices of a truncated octahedron that is still embedded in 4 dimensions. Finally, we make this structure visible. The vectors u, v, w span the 3-dimensional cell inside our 4-dimensional space. From u, v, and w, we can construct 3 orthonormal basis vectors. Projecting all cell vertices onto this basis gives 3 coordinates per point, which allows us to interpret them as points in ordinary 3-dimensional space. Plotting these coordinates reveals the familiar geometry, a truncated octahedron appearing here as one cell of the larger 4-dimensional structure generated from our seed point. And with that, the abstract machinery resolves into something tangible. That's all for today. I hope to see you again. Bye bye.